I now call to order the Society's 2434th meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone, and welcome to PSW Science's Spring 2021 meeting and lecture series. I'm Larry Milstein, President and Program Director of PSW Science, one of the oldest scientific societies of Washington, D.C., founded in 1871 as the Philosophical Society of Washington. In order to accommodate our speaker's schedule tonight, we will forego the usual preliminaries and go straight to the lecture. Tonight's speaker is Avi Loeb. Avi is Frank Baird Professor of Science at Harvard University, Director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics, and a director of Harvard's Black Hole Initiative. His lecture tonight is on the search for extraterrestrial life. And the question, just how smart should we think we are? The smartest cookies in the cookie jar? He is joining us tonight from the Boston, Massachusetts area. All questions will be fielded in a Q&A session after the lecture. Avi, the screen is yours.
Thank you very much, Larry. Let me share the screen. It's a great pleasure to visit Washington, D.C. virtually. And I have a new book that just came out a week ago. And by now, after the first week, it's listed on the New York Times bestseller list, number 7. And there should be a review in the New York Times that you will find in the weekend edition. So let me briefly mention the phrase that characterizes the discussion in this book. When you are not ready to find exceptional things, you will never discover them. This is an excerpt from a Scientific American article that I wrote a few months ago. And it pretty much summarizes the content of the book called Extraterrestrial. What you see on the left is an image, a photograph of a photograph that was presented in Berlin just a few months ago by the photographer Herlinde Kubel, who came to visit me at my office at Harvard, asking me to write on my hand the most important question that I can think of in the context of my scientific research. And I wrote, "Are we alone?" So let me start by explaining my underlying sense of cosmic modesty, that after several decades of working in astronomy, the biggest message I received from the universe is that we should be modest. So let me explain by reading these 2 paragraphs. And basically the book resulted from my experience after both my parents passed away over the past few years. My father, David, was laid to rest in the same red soil in which he planted trees all his life, in the vicinity of those plantations that he watered routinely, near the house that he built with his rugged hands, and that I grew up in, surrounded by the people he loved and who loved him in return, under the blue sky that I study as an astronomer. My mother, Sarah, who put me on the road to thinking as a philosopher, with whom I spoke daily throughout my adulthood, and who especially gifted me with a life of the mind, was buried beside him 2 years later. In astronomy, we realize that matter takes new forms over time. The matter we are made of was produced in the hearts of massive stars that exploded. It assembled to make the Earth that nourishes plants that feed our bodies. What are we then if not just fleeting shapes taken by a few specks of material for a brief moment in cosmic history on the surface of one planet out of so many. We are insignificant, not only because the cosmos is so vast, but also because we ourselves are so tiny. Each of us is merely a transient structure that comes and goes, recorded in the minds of other transient structures. And that is all. And so when looking at the universe, we know that there are more habitable Earths in the observable volume of the universe than there are grains of sand on all beaches on Earth. And so I have a hard time understanding those alpha males that were portrayed in illustrations like this one being very proud of conquering a piece of land or leading a country. We know that about half of all sun-like stars host an Earth-sized planet in their habitable zone. So, and that is from the Kepler satellite, just a paper that came out a few months ago. And so the conditions we find around us are replicated in many other places. And that gives me a sense of cosmic modesty. Not only that we are not at the center of the universe, as advocated by the ancient Greek philosopher Aristotle, and of course that was flattering to the ego of humans to hear that message, and this model of us being at the center was endorsed for 1,000 years before Galileo and Copernicus argued that actually the Earth moves around the sun. But not only that, now we know that the conditions in our backyard, the Earth-Sun system, are quite common. They're not unusual in any way. So we are not privileged. We should have a sense of modesty. Those emperors and kings that conquered a piece of land on Earth just resemble an ant that hugs a single grain of sand on the landscape of a huge beach. And we can sort of understand where it comes from, this arrogance that humans often exhibit. When my two daughters were young, they tended to think that the world centers on them. You can see them in the picture here. And of course, once they went to the kindergarten, they met other kids and realized that, in fact, those kids have qualities that are superior to theirs. And so they developed a sense of modesty. They might have preferred to stay at home and live the fantasy that really their qualities are not replicated anywhere. And that's what many of my colleagues, scientists, prefer to believe in. They ask me to provide them with extraordinary evidence that technological civilizations exist out there. To me, that sounds like the default position. Conditions on Earth are replicated elsewhere. Therefore, the outcome of those conditions should be similar to what we find here on Earth. That is the common sense approach. And we should just search for the signatures of those civilizations rather than convince ourselves that we are unique and special, like my daughters thought when they were at home. And our civilization will mature only by leaving home to go to the cosmic street and meet others. And frankly, I don't think we are the sharpest cookies in the jar. And by the jar, I mean the Milky Way galaxy. So there are billions of Earth-Sun systems. And judging by the news that we read every day, it's hard to believe that we are the most intelligent ones in that jar. We make a lot of mistakes. We put most of our resources in conflicts. We do not cooperate towards a better future. We exhibit throughout human history ideas that do not make any sense, that allow some people to feel superior relative to other people. But when you see the big picture, the universe at large, all of these competitions on Earth make very little sense. You know, how can the color of a skin of a person make any difference in the big scheme of things? So we are definitely not the most intelligent you can imagine. Moreover, you know, if you've opened recipe books, you realize that you can start from the same ingredients and end up with very different cakes, depending on how you mix those ingredients. And it's hard to believe that random processes on Earth ended up making the most tasty cake possible. Earth is our home, but only for a while. Because of internal threats, we create technologies that could kill us. We could change the climate. We could go into wars. There are pandemics, there are political catastrophes that could take place. We had our technologies for about a century. And typically, you know, statistically speaking, when you find any object, like a person or anything, you often find it in the middle of its life. And that would argue that probably we have a few centuries left, unless we get our act together and make an effort to survive longer, given those technologies. There are, of course, external threats. An asteroid impact. 66 million years ago, the dinosaurs saw this giant rock, roughly the length of Manhattan Island, approaching them and getting bigger and bigger on the sky. It was a fun event to watch until the rock hit the ground. And then 3/4 of all species of life went extinct after that. Of course, the dinosaur had much larger bodies than we have, but turns out that our brain is much more useful for survival. So we have astronomers, and the astronomers can use telescopes to warn us of an incoming rock and to prevent a similar catastrophe. And indeed, Congress tasked NASA to find 90% of all the near-Earth asteroids that could be bigger than 140 meters. And one of the early telescopes that was designed for that purpose, serving the sky, is called Pan-STARRS. There is another one coming online in 3 years called the Vera Rubin Observatory. Pan-STARRS is in Hawaii, and the Vera Rubin Observatory will be in Chile. So let me say a few words about my history, which is described in the book as well. How I was born on a farm in Israel, and you can see me on the top left here. I used to collect eggs every afternoon. You can see me here doing that in the second image. And by the way, this provided me always with plan B. I was never worried about getting tenure at Harvard because I could always go back to the farm. And actually, in retrospect, I'm not sure that my life wouldn't have been happier being embedded in nature rather than in a crowd of competitive academics. And you can, in the middle photo, you can see me on a tractor with my sister. I used to drive a tractor to the hills of the village every weekend and read philosophy books. That was my passion. I was interested mostly in the deepest questions we have about life. And then circumstances brought me to astrophysics. I was involved in the Star Wars initiative back in the mid-1980s. I led a project that was the first international project funded by Reagan's initiative. And that brought me to Washington, D.C. quite often. And then in one of the visits, I went to Princeton and eventually was offered the 5-year fellowship under the condition that I'll switch to astrophysics. Afterwards, I met my wife. You can see that on the right, and we have 2 girls. So I'm surrounded by women, and that's my biggest gift in life. In 2015, an entrepreneur from Silicon Valley named Yuri Milner came out of a black limousine and entered the Center for Astrophysics, where my office is located, sat on the sofa in my office and asked whether I'm willing to advise him on an initiative to visit the nearest star system within our lifetime. And since the nearest star is Proxima Centauri, 4 light years away, I mean, it takes light 4.25 years. And in fact, the results of the 2016 elections are getting there only this month. Since it takes 4.25 years to get there for light, you really need a spacecraft that travels at 1/5 of the speed of light if you wanted to get there within a couple of decades. So I told Yuri, I need to think about it for 6 months and figure out whether it's feasible. Is there any technology that we can use that would bring us to a fraction of the speed of light? And we ended up working with my students and postdocs on various technologies and concluded that the only one that appears feasible in principle is a light sail. And I'll describe it in a minute. And that was announced as Project Starshot in April 2016. Stephen Hawking came for the public announcement in New York City. So here is a diagram of the solar system. The sun is on the left. And at roughly 10 times the Earth-Sun separation, you find Saturn. And then to the 100 times the Earth-Sun separation, that's where the solar wind, the wind that comes out of the sun, is stopped by the interstellar medium, the gas that fills the void between stars. But the solar system extends well beyond this boundary, which is called the heliopause. The solar system goes out to 100,000 times the Earth-Sun separation with a so-called Oort cloud, which is a collection of rocks covered with ice that when they happen to move towards the sun, they appear as comets, long period comets. And they are just leftovers from the formation process of the sun and the planets. You can think of them as Lego pieces that some of which were used to make up the rocky planets, but some of the Lego pieces were left intact and remained and were scattered afterwards into roughly a spherical region around the sun. And that's the Oort cloud. And it extends roughly halfway to the nearest star. So in fact, if you imagine the nearest star, Proxima Centauri, having an Oort cloud roughly of the same size, then Oort clouds touch each other. They are just like billiard balls that are densely packed in space. And so stars passing near each other can easily rip apart those loosely bound rocks and make them a population of interstellar objects. Proxima Centauri happens to have a planet next to it. It's a dwarf star, and the planet is 20 times closer to that dwarf star. The star has 12% of the mass of the sun, and it's much fainter than the sun. It has roughly half the surface temperature of the sun. So it emits mostly infrared light. And the planet is so close that it has a permanent day side. It's tidally locked. Just like the moon shows us only one side, this planet most likely shows one side to the star. So there is a permanent day side and a permanent night side. My daughters say that they would like to have a house on the permanent sunset strip, which probably has the highest real estate value because you can see the sunset forever if you have a house there. Another thing to keep in mind is most of the light is in the infrared. So if there are any creatures on the day side, they have infrared eyes. This may explain why they never visited us, because interstellar travel agencies would never advertise the Earth as a desired destination. We have green grass and visible light from the sun. They have red, dark grass. And they don't want to hurt their sensitive eyes by coming to Earth. So in order to entice them to visit us, we will probably have to go there and offer them a water-based drink and ask them to come and visit us. And in order to get there, that's a long journey. If we were to use the existing rockets, it would take 50,000 years. So we had to send these rockets when the first humans left Africa in order for them to get there now. We are not that patient, especially Yuri Milner is not that patient. So the question is how to get a spacecraft to a fifth of the speed of light so that it will reach Proxima Centauri within a couple of decades. And the only technology that seemed to work is that of a light sail. Think of it just as a sail on a boat, except it's being pushed by light rather than the wind. So light bouncing off a mirror or of a thin surface would give it a push. And to get a significant push, you need first the sail to be lightweight, but also the beam of light to be very powerful. And so the idea is to use a very powerful laser of about 100 gigawatt focused on a sail that has roughly the dimensions of a person, a few meters. And if the sail weighs of order a gram and you shine the laser for a few minutes, you can reach a fifth of the speed of light across a distance that is roughly 5 times the distance to the moon. And that's the concept that we came up with. And you can put on the sail some electronics that would weigh less than a gram, that include a navigation device, communication device, and a camera, such that it will take a picture, a photograph of Proxima B when it gets there. This technology of a light sail was already demonstrated by the Planetary Society. You can see that on the image on the right. That's a light sail that is using solar light, starlight, sunlight. So here is the concept in a video. There are lots of low power lasers that produce beams that are combined into this powerful laser beam. And then the sail is released above the atmosphere so that it will not encounter friction. It's released from a mother spacecraft, and then the beam shines on it and accelerates it to a fifth of the speed of light over a few minutes. And then after that, there is this long and boring journey that takes 20 years. So a few minutes for the acceleration, for the launch, and 20 years for the trip. And this trip is relatively boring. I mean, you just cross empty space most of the time. And then the hope is that the sail will get to the vicinity of Proxima Centauri and its planet and take a photograph of the planet and then transmit the signal, the photograph, back to Earth. And then it will take another 4 years for that signal to reach us. So altogether, 24 years. That's a long time. And also, because of the vast distance, the signal will be very faint. So you need a telescope to detect it. This is the concept. And we are currently working on the various elements of this concept. But the fundamental question is not so much whether there is life on Proxima B, perhaps primitive life. The real question in my mind is, are we the smartest kid on the block? And as I said before, Earth may have not baked the best possible cake. So without a prejudice, we should be open-minded and search for evidence. Rather than assume it's never aliens, it's always rocks, we should look around. And the best place to look is actually in our backyard. And we can move outwards afterwards. And the advantage of our backyard is you don't have to travel very far, you just look around, sort of like looking for an object that came from the street into your backyard at home, and instead of going into the street itself, because that takes time. And the first object that we recognized in the solar system that came from outside was named Oumuamua. It was discovered on October 19th, 2017. And this name means a scout in the Hawaiian language. This name was given to it because the telescope that discovered it, Pan-STARRS, that I mentioned before in the context of the dinosaurs, that telescope is on the summit of Mount Haleakala in Maui, Hawaii. What you see in the image is this object. It's a very small object, roughly the size of a football field, a few hundred feet. So we cannot resolve it with any telescope on Earth. We just saw a point of light, which is circled in blue here in this image. And what you see as trails of dots are stars in the background. So if you keep your eyes focused on the object, the stars are moving relatively fast across the image. And that's why you see a sequence of dots that represent different snapshots. And this is the trajectory of this object on the sky. And those of you who are amateur astronomers will recognize what is written in purple letters here, the solar apex. Now, what that is the direction that the sun is moving in the so-called local standard of rest. The local standard of rest is the frame that you get to when you average over all the random motions of the stars in the vicinity of the sun. So every star has some velocity relative to this frame, and then you average the velocities of all the stars near the sun, and you get to the local standard of rest. You can think of it as a sort of a public parking lot. And the sun is moving in the direction of the solar apex in that frame. Now, the amazing thing is Oumuamua was at rest in that frame. Only 1 in 500 stars is at rest, as much as Oumuamua was in that frame. So finding an object that doesn't move much in that frame is quite unusual. And Oumuamua was one of these objects. And that's by itself a remarkable coincidence and surprising, because this is really the first object we found. And the relative velocity of us and Oumuamua is simply because of the motion of the sun relative to the local standard of rest. But also it implies that we cannot really tell which star Oumuamua came from, because all the stars are moving. And if Oumuamua came from one of them, it should have inherited the velocity of the parent star. But there is no star that is that slow relative to the local standard of rest. So we don't know where it came from. Just like finding a car parked in a public parking lot, you don't know which house it came from. And this is the path of Oumuamua relative to the sun. So the sun moved in its direction, and that's the origin of its initial velocity. And then it was scattered by the gravitational force that the sun exerted on it when it came close. So it's sort of like finding a buoy at rest on the surface of the ocean, and then the solar system was like a giant ship that bumped into it and kicked it. And we couldn't resolve this object, as I mentioned, but we could measure how much light is reflected from it. So you should think of the sun as a light post that is illuminating the object. And then as the object tumbles, as it spins, the amount of light reflected changes. And it changed by a factor of 10. That's unheard of in the context of asteroids or comets. Usually you get a change by at most a factor of 3. And it implies that the length of the object projected on the sky was 10 times longer than the width of the object projected on the sky, at least, if not more. And moreover, if you try to fit the light curve, the best model is that of a flat object, pancake-like, at the 90% confidence. Despite what you saw in a cartoon about this object that shows it like a cigar. I mean, when projected on the sky, It looks elongated like a cigar, but intrinsically it's flat based on the light curve, like a pancake. And this is the orbit starting from the top and going to the left. So in July, the object was approaching us. It so happens that my family and I visited Maui for a vacation in July 2017. And I was asked to give a seminar at that observatory. So I actually was on that mountain peak in July 2017. Back then, we didn't know about Oumuamua. We only found it on October 19th, which is on the left of this trajectory here. And it was receding away from us at that point. You know, if we were to detect it on its approach to us, in principle, we could have sent a camera that would intercept its orbit and could have taken a photograph. A picture is worth 1,000 words. It would have saved me from writing this book, because if we had a photograph, then we could have said what the nature of this object is. Without a photograph, you know, we don't know for sure. But that's a lesson for the future. If we discover other objects that are as weird as Oumuamua was, we better take a photograph. That's my main point, actually. And so why do I say that? Because this object was very weird. I already mentioned some properties that are unusual, but actually the first one is the fact that we actually detected it. A decade before this object was discovered, I wrote a scientific paper with two collaborators, Amaya Moore-Martin and Ed Turner, that calculated how many interstellar objects should we expect based on what we know about the solar system. So imagine that all other planetary systems are just like the solar system. You can then estimate how many rocks will be kicked into interstellar space, mostly from the outer parts of those planetary systems, because there they are loosely bound and passing stars can easily rip them apart. And we estimated that pan-stars would see nothing by several orders of magnitude. So the fact that they detected Oumuamua was a real surprise to me. But also it was sitting in the local standard of rest. Again, a chance in 1 in 500. And then its brightness changed by a factor of 10 as it was spinning up, or tumbling. And that implies an extreme shape, most likely pancake-like. You have to understand all of these properties make it quite unusual. There was no heat detected from it by the Spitzer Space Telescope. We know what was its surface temperature because we know its trajectory. And the temperature to which a body is heated is dictated only by its distance from the sun. So given its trajectory, we know the temperature that the object had. And given that the Spitzer Space Telescope didn't find any infrared emission from it, we can set an upper limit on its size. It must be smaller than something so that the amount of heat radiated would be smaller than the detection threshold of Spitzer. And so that implied that the size must be smaller than about 200 meters. And given that if it were 20 meters in size, it would have to have a reflectivity of order 100%, because we detected how much sunlight is reflected off it. This implied, this upper limit on its size already implied that it's relatively shiny at the higher end of reflectance from objects that we find in outer space. But the most unusual property of this object was that it deviated from an orbit that is shaped by the sun's gravity. And it did so without having any cometary tail, any evaporation. So usually for comets, you get the rocket effect. When gas evaporates, it pushes the comet in the opposite direction, away from the sun. But there was no such outgassing. Nothing was detected, no carbon-based molecules, no dust. And so the question was, what gives it this extra push? And if it were a comet, you needed about 1/10 of the mass of this object to get evaporated, 10%. So that's a lot of gas out there, and we would have noticed it. The only alternative I could think of for pushing it is reflection of sunlight, just like you have in the case of a light sail. But for that, the object indeed needed to be very thin, like a light sail. So I wrote a paper suggesting that the object is a light sail. And this suggestion was very similar to other suggestions that I made in the context of the early universe in my career, or black holes. Whenever faced with an anomaly, you try to suggest potential solutions. And this was a potential solution to the anomalies of it having a flat shape and being pushed by sunlight. But of course, the media immediately noticed. This paper was accepted for publication within a few days. It was written with a new postdoc of mine, Shmuel Bialy, and there was a huge response to that. But in the couple of years after that, some mainstream people tried to find other solutions that rely on a natural origin. I should say the astronomy community divides into 3 components. The one component is those people that write blogs or popular science books. They are very well known to the public. But if you check the archive of scientific papers, you will not find a single paper that they wrote over the past decade. So I don't even pay attention to what they say, because they're not practicing scientists. Then you have the biggest chunk of the scientific mainstream, people that are not familiar with the details of rocks in the solar system and what to expect and so forth. So they just say, I don't worry about the details. It's probably natural. It's never aliens. Forget about it. Business as usual. And then you have those people that pay attention to the details, to the anomalies that I mentioned, and they try to find a solution. And those are the people that I respect the most. And the kind of proposals that were made to explain the properties of this object are as follows. They always invoke something that we have never seen before. So on that, everyone agrees. It's nothing that we have seen before. And the proposals are, perhaps it's a dust bunny, like you find at home, a collection of dust particles in a cloud that is 100 times less dense than air. Let me repeat, 100 times less dense than air, floating in space, reflecting sunlight, and being pushed by it. The question in my mind is whether such a structure that is 100 times less dense than air can survive the journey of millions of years through interstellar space and tumble over an 8-hour period. Can you have such a structure that maintains its integrity? I have strong doubts. Then there was a suggestion, maybe it's a fragment from the tidal disruption of a bigger object near a star. The problem with that is usually tidal disruption results in shrapnel or pieces that are elongated like a cigar. But at the 90% confidence, this object looked like a pancake. So this explanation cannot hold. And also the chance of passing close to a star is very small. Most of the objects will never pass close to a star. So if you find the first object, it should represent the more typical conditions, not extreme conditions like passing near a star. And then there was a suggestion, maybe it's an iceberg made of hydrogen. And the idea here is you can get the rocket effect by evaporating such an object, but hydrogen is transparent, so we won't see the cometary tail. The problem with this suggestion is that hydrogen can get evaporated very quickly. And we showed that in a follow-up paper demonstrating that such an iceberg will not survive the journey. And the authors of this suggestion, this paper that suggested it, agreed with us. So here you have it. People that try to solve the challenges imposed by the anomalies of Oumuamua had to invoke something that we have never seen before. So if we do that, why not an artificial origin? Why not a light sail? Why not a piece of technology? And this is an excerpt from the first review of my book on Goodreads that uses words that I've never heard of. I asked my daughters and they explained it to me. And one way to think of Oumuamua is like a plastic bottle among natural seashells. When you walk on the beach, you see mostly rocks that resemble the asteroids and comets that we have seen. But every now and then you might find a plastic bottle that indicates that there is a civilization out there that produced it. And it will not be functional most of the time. It will have holes in it. And in the case of space, it could be just space trash. Voyager 1, Voyager 2, New Horizons, they look like very impressive pieces of technology right now, but imagine them in 1 billion years. And most of the stars in the Milky Way galaxy formed billions of years before the sun. So imagine all the trash that was deposited in interstellar space. Most of it will not be functional. It will be just pieces of equipment that are floating out there and do not serve any good purpose. Now, it turns out that a few months ago, in September 2020, there was another object, and here you can see the orbit of this object around the Earth, not around the sun, around the Earth. The Earth is moving around the sun, and this object is moving around the Earth. Turns out that, so this object was given the astronomical name 2020 SO by the Minor Planet Center at the Center for Astrophysics, and that's before it was clear where it came from. This object exhibited an extra push away from the sun by reflecting sunlight, and it didn't have a cometary tail, just like Oumuamua. Turns out that one can trace this object to a rocket booster that was kicked into space in 1966. And the only reason it showed this extra push is because it's very thin. It's hollow. So we know that we produce this object and that it's artificial. The question is, who produced Oumuamua if it resembles this object? The point about this detection is it was discovered by Pan-STARRS, the same telescope, and it shared properties with Oumuamua. We can tell the difference between a very thin object and a rock based on the way they move. And there was a second interstellar object called BORISOV. It was discovered in 2019 by an amateur astronomer from Russia called Gennady Borisov. This one looked just like a regular comet. No difference from the comets that we have seen before. So people came to me and said, oh, if Borisov looks like a comet, doesn't it convince you that Oumuamua was also of natural origin? And to that I said, you know, if you see a plastic bottle on the beach, and after that you see natural rocks, that doesn't mean that the plastic bottle is a rock. Or another way to put it, when I met my wife, at first I thought that she's special. Since then I met a lot of people, and I still think that she's special. So in fact, the discovery of Borisov strengthens the case that Oumuamua is unusual, because this one is just a natural object, and the other one is really strange. What is it? Who made it? On the left here is the artist's impression, which is incorrect, as I mentioned before, because it should be a flat object. And you know, we came to exist relatively late in the history of the universe. The sun was formed 4.5 billion years ago, out of the 13.7 billion years of the universe. And our technological civilization ages just one part in 100 million of the entire age of the universe. So we really came to exist as a technological civilization very recently. And if there are such civilizations around most of the sun-like stars, or a substantial fraction of the sun-like stars, then they were much older than us by billions of years, because most stars formed before the sun. And of course, near them, depending on the temperature of the star, there is the so-called habitable zone where you can have life, liquid water and life. And we could search for technological signatures. One can search for industrial pollution in the atmospheres of planets. One could search for megastructures, big structures surrounding either the star or the planet. Or one can search for a beam of light that is used to drive light sails, just like the Starshot project. But there would be some leakage of the light, and you would see the beam sweeping across the sky as a flash of light when it crosses us, just like a lighthouse. You can look for photovoltaic cells covering the day side of a planet, or you can search for artificial lights on the night side. We have been searching mostly for radio signals. That's not a smart move, because radio signals are just like a phone call. You need the counterpart to be alive in order to have a conversation. But if you're waiting for a letter in the mail, given that USPS is very slow sometimes, the person who sent the mail may not be around anymore, and it doesn't really matter. So if you get a message in a bottle, like Oumuamua, then the civilization that produced it could be dead by now, but nobody cares. So the Drake equation doesn't really apply to physical objects. All you need to know is how many plastic bottles you have per unit area on the beach. And then you know the chance of seeing one of them next to you. In terms of getting sails close to the speed of light, it may not always be necessary to produce a very powerful laser. One can use a natural light source. Imagine a massive star that is about to explode. Such an explosion is called a supernova. It's brighter than the entire galaxy when it happens, depending on the size of the galaxy. And if you park light sails at 100 times the Earth-Sun separation from a massive star, they would reach near the speed of light as a result of the flash of light that comes from the explosion. So just like surfers in Hawaii waiting for the wave to come in so that they can ride it, you can put light sails around a massive star and surf on the flash of light coming from the explosion. It's just like dandelion seeds blowing in the wind that you can see on the right here. And you can fill the galaxy with light sails this way, moving relatively fast. Of course, pan-stars would never notice something moving close to the speed of light. The observers will just dismiss it. So Enrico Fermi, a very famous physicist, when he was in Los Alamos, one time at lunch, he said, well, it's indeed quite likely that there might be a lot of technological civilizations out there. Where is everybody? Why don't we see them? Well, the point is, once again, when I met my wife, she had a lot of friends that were waiting for a prince on a white horse to meet them and make them a marriage proposal. So that assumes something, right? And it never came. And why would our civilization be so attractive that someone from outside would care to visit us? we're probably very typical. We're just like ants on a sidewalk. If you walk down the street, you don't pay attention to every ant. So one possible solution to Fermi's paradox is that we are not interesting. Clearly, we are not very intelligent if you look at the history of humans. You could imagine another possible solution, and I came across it. Well, first of all, that other civilizations may be short-lived, just like we might be, because they produce the means for their own destruction. But I came across another solution during the pandemic. Perhaps there is social distancing on a cosmic scale. So imagine a very advanced civilization that creates its own habitat. It may close itself off in a cocoon and never interact with lower level civilizations, because that would only lower its quality of life. Why would it worry about us? That doesn't mean that we cannot learn about their existence, because according to the second law of thermodynamics, they produce trash. And just like investigative journalists that go into the trash cans of celebrities in Hollywood, we can search through their trash and figure out what their lifestyle is about. But perhaps they are dead. We can still search for the relics they left behind, either in the form of objects floating in space like Oumuamua, or by relics that are left on their host planet. I call that space archaeology. So we can't have a phone conversation with the Mayan culture because it's not around anymore. But we can find the relics through an archaeological dig. And the same can be done in space. We can search for technological relics in space. We can search for megastructures, polluted atmospheres, and relics flying through space. And my hope is that by finding relics of civilizations who perished as a result of a climate change or war, we would learn an important historic lesson to get our act together and avoid a similar fate. We could also learn about their technologies and import them to Earth. And if their technologies are millions of years more advanced than ours, it would feel like cheating in an exam, looking over the shoulder of the student next to you. But if it saves us 1,000,000 years, it may be worth it. So on February 18th, in a couple of weeks, the Perseverance rover will land on Mars. And we will be able to explore the conditions on the surface of Mars and try and figure out if there was life on Mars. So the search continues, it's ongoing. And if we find life on Mars, it would be primitive life. What I'm most curious about is intelligent life and whether we can learn from them, whether we are the smartest kid on the block. Thank you very much.
Thank you, Avi. So we have time for a Q&A session. So with that, let's see what we have coming up. So Mike Helton, if you'll unmute your mic, you can ask a question.
Yes, thank you. And that was a very informal and a very informing lecture. I appreciate it very much. As you may know, there was a project called Project Lyra, which was designed to make a probe to go chase down Oumuamua and take some photos. Do you know of that project, and do you know what the status of that project is?
Well, I don't think it makes sense anymore, and I'm not sure it made sense back when it was proposed. Oumuamua was moving relative to us at a speed larger than the rockets that we have, and right now it's actually 1,000,000 times fainter than when it was close to the sun. So you would need to equip any spacecraft that is chasing it with a big enough telescope so that it can find it. We don't know the trajectory of Oumuamua precisely enough to forecast in advance where to go. We need to see it. And frankly, it's not worth chasing it because we found this object over a few years, and there would be another one within a few years if you take the Copernican principle seriously, that we don't live at a privileged time. When I go to the kitchen and I see an ant, I get alarmed because I know that there must be many ants in the kitchen. And so finding one object over a few years with Pan-STARRS implies that if Pan-STARRS continues to look for a few more years, it will find another one. And in fact, there is the Vera Rubin Observatory that will be much more sensitive and is expected to find one every month. So what we need to do is wait for the next weird one to show up, something that doesn't look like a comet, that has similar anomalies as those of Oumuamua, and then study it in great detail.
Okay, thank you.
Just a note for those of you who don't know, the Vera Rubin was previously called the LSST, and we had a talk on it not long ago by the project manager. So if you wanted to watch a video on that.
Yeah, I should say that one risk to this project is the communication satellite constellations that SpaceX is launching. There will be tens of thousands of them. So unless they paint them dark, black, so that they don't reflect sunlight, these would produce streaks in the images of the sky that we get from LSST. And that poses a major issue for astronomers.
Yes, hopefully they'll work it out. I understand they're discussing with SpaceX and the astronomy community how to solve the problem.
Yes.
So a question from Carl Merrill. Carl.
Thank you. I really enjoyed that presentation. I read part of your book. I wanted to finish it, but I didn't get to finish it yet. I will. I'm a physician, but I never practiced medicine because when I was a young person, I found the book and I read it over and over and kept it under my pillow. And the title of the book is What is Life by Schrodinger. And so I've spent a lot of my career trying to understand what life is. I went to Cold Spring Harbor and I worked in molecular biology. And I've thought a lot about the questions you've asked and launching that sale and deciding what's out there. So I want to make a proposal, and I'd like your opinion of whether you think this is a viable way to approach this. The problem I have with the sales is that when they get out there, you still won't know whether you have ants out there or intelligent life. So what I'm suggesting is that you send out, instead of sales, just little tiny particles that are universal constructor machines. In fact, that's exactly what we are. And you can have really small ones like radiodurans that can withstand tremendous radiation. So there's a good chance they could travel a long distance. If they find anything that's habitable, they'll land on it, and by probability and random laws of mutation, they'll eventually evolve to the point where they can control not just the electro weak force, but they'll begin to explore other things. At that point, they've achieved some intelligence. That's what you really want. And you can look for them because then on any single planet, you'll see a spectral signature of a thermonuclear device or something going off. So it would make a nice assay for it. I just wanted to bounce that off and see what you think of that.
Well, yeah, there are many possibilities. We can imagine things that resemble what we find here on Earth, but the realm of possibilities is vast. And one way to improve our imagination is to conduct laboratory experiments. So we could potentially create synthetic life under different conditions and see an experiment with it. Or we can go places and see what's out there. With respect to Oumuamua, I should mention it's an object, physical object, the size of a football field, and we wouldn't know what its purpose is until we really study such objects in detail. And as to what produced it, that remains to be seen. And as to what is the most common form of life, again, I think we better approach it by seeking evidence rather than trying to guess, because we've been wrong so many times before.
Let's take a question from Dick Garwin. Dick, you're on.
Yes, can you hear me?
Yes.
Okay. I'm worried about the required uniformity of the foil because you have to have something like 10,000 times the acceleration of gravity at the surface of the Earth to accelerate to a tenth the velocity of light in a few hundred seconds, a few minutes. And if the foil is not absolutely uniform in reflection coefficient and in density or thickness, it will tear. So how is that managed?
Yeah, so we checked it, and we're talking about 100,000 G, where G is the acceleration on the surface of the Earth. And you can definitely have materials that will withstand that. And another challenge for the materials is that it needs to reflect the light at a very high level. Only one part in 100,000 of the light impinging on the material can be absorbed, because otherwise it will burn the sail. We're talking about a high power laser, and so that's another challenge. It needs to be very reflective, and there are materials that would serve the purpose that are stiff enough. And I can send you a paper. If you send me an email, I'll share with you.
Well, but that's not the point. The point
I know what your point is, but the answer is there are materials that will sustain the acceleration that is imposed.
No problem with the acceleration. The problem is the uniformity.
Yeah, and they will be uniform.
And if it's crinkled, you have the same problem. Okay, I will write you. Thank you.
Yeah, send me an email and I'll share with you some information.
Thank you.
We have Joel Wilson, a question. Joel?
Yes, hi, Professor. Thank you for your lecture. It was very, very interesting and challenging, I think. I was wondering, in terms of detecting interstellar objects, you mentioned that the LSST would run into some problems, but isn't the LSST and the James Webb supposed to be, in a certain sense, connected in terms of some of their data processing? And I'm wondering if that could address some of the issues.
Not really, because the field of view of JWST is only a few arc minutes. It's about a tenth of a degree. And the whole idea of LSST and Pan-STARRS is serving the entire sky, not focusing on a small field of view. But once you find an object, of course, JWST can point in that direction, but it will not be useful as a survey telescope. It will be useful to examine the properties of an object that you find with LSST. So yes, you're right that they could be complementary, but only after you detect an object.
Right. And also, if I might say, I was very touched by your beginning story of your parents.
Oh, thank you.
I'm not so sure that my two parents and your two parents didn't go to the same school by the way you speak of them. I just recently lost my father. So I'm very touched by stories of one's parents and how they impact each other. So thank you for sharing that, sir.
I mean, if I had to summarize, I was asked by one of the reporters, I had about 150 interviews over the past few days, over the past few weeks about my book. And one of the reporters asked me, what did you learn from your mother and what did you learn from your father? And my answer was that, of course, with my mother, I used to speak every day and I learned to think abstractly in philosophical terms about the big picture. From my father, we didn't exchange a lot of words, but I learned that what matters the most is doing things rather than speaking about them. So just to illustrate it with an example, over the past 6 months in academia, there was a lot of discussion about how to help underrepresented minorities in getting academic positions and so forth. There were lots of Zoom meetings organized on that a lot of people attended. But the same people that organized these meetings, just a few months earlier, when I asked them to help me with specific individuals, they were not very helpful. And that to me illustrates a problem where people portray an image as if they care about the subject, whereas in reality, they don't really apply the same principles when dealing with real people. And what I learned from my father is that it's more important to do things than to talk about them.
Yes. Thank you, sir.
I have a question from Todd Powell. Todd?
Good evening. Sorry about that. I thought that you might just read it off of there. No, I was fascinated by your topic, and I've been a lifelong, I'm a historian, and so, but it has always been a subject that was close to my heart, and I followed the Project Orion nuclear as a youth, and I understand that because of the various treaties, it was disregarded. Is something like that ever come back as a possible option? A quick UN treaty and we're off on our way?
Not really, because taking nuclear material into space is a very delicate issue. People are worried about the fallout if the mission is not successful, and it's not really practical at this point to take a nuclear reactor into space, or even worse, to take bombs that will explode and power an engine like the Orion project was about in the days of Freeman Dyson. And back then they to demonstrate the propulsion mechanism, they took some explosives on a flight. They put it in the overhead bin on a flight to California. Imagine doing this now.
Quick follow-up.
It's just not politically, it's not practical at the moment to entertain such ideas, because people are worried about what happens if it fails, and then you have one nation launching a nuclear reactor that falls on another nation, and it's worse than Chernobyl, which happened in the same state that
And again, I followed both that, and again I followed the whole Skylab imbroglio as well when that returned prematurely. And then two quick questions. And I understand too, there was a lot of work that was still done through the 60s on this, and then some of the work that was done in the 90s as well. And I didn't know if either of those were things that you looked at or considered.
Yeah, I looked at nuclear. I mean, there is also some work in Russia on perhaps nuclear, and didn't look practical to me. Also, you don't get to a fraction of the speed of light, because nuclear energy is not sufficiently, you don't get as much energy per unit mass that will bring you to that. The ultimate speed that you reach is just dictated by the energy that you get out per unit mass of fuel, because all of the conventional methods for acceleration rely on fuel, and the spacecraft carries the fuel. Right. So what you care about is how much energy per unit mass. That you take the square root of that, it gives you a characteristic speed, because energy, the kinetic energy, is the mass times 1/2 v squared. So when you get that speed, you can't accomplish a speed much larger than that, and that is usually much less than 1/10 of the speed of light for all kinds of nuclear reactors. But I should say that with the light sails, of course, the advantage is you're using light, so you can reach the speed of light, and you don't need to carry the fuel. So it's a completely different method in that regard.
I love your method, and I think the aspect of the kinetic question is a big part of that. And I know that then you would talk about a dramatically larger craft, going back to the Orion, and to try and answer the kinetic question, it then became a scalable issue, and you're talking about a generational ship as well. But again, a different logic thing. Thank you very much for answering and rejoinder.
Thank you. And of course, once we monitor vehicles that were sent by others, we can see what they used. That would be a useful lesson.
I have a question or two from Colin Alberts. Colin?
Good evening, Professor. I wanted to ask you, you mentioned Freeman Dyson a couple of seconds ago, and I wanted to sort of carry him off that to ask about extraterrestrial advanced civilizations engineering and whether they would be detectable. There's been speculation that if there was a Dyson sphere created out somewhere in the galaxy, we would be able to detect it if a star that wasn't in that, isn't in that phase of its life cycle suddenly flickered out.
Right.
Are there any other sort of interstellar architectures that we could, engineering that we could detect? For example, if if some other civilization figured out how to use an Alcubierre drive, would we be able to detect it's being used somewhere, anywhere, in near space or anything like that?
Right. So, well, first I should confess that Freeman played an important role in my career because in one of my visits to Washington, I decided to visit the Institute for Advanced Study at Princeton, and the administrator allowed me to go there and said that people are very busy, except for one person, Freeman Dyson. He has a lot of time. So why don't you go and speak with him? And I went, and he introduced me to John Bakal, the astrophysicist, who was married to an Israeli. And he said, he likes Israelis. Why don't you meet him? And I didn't know how the sun shines. I didn't know astrophysics at all, but John gambled and offered me a 5-year fellowship. So I pretty much owe my career to Freeman introducing me to John, who offered me a fellowship at Princeton that led to my current appointment at Harvard. And I served as the department chair at Harvard in astronomy for 9 years, for the past decade. With respect to your question, yes, indeed, Freeman wrote a very short paper. He was very imaginative. And in that paper, he argued that, in principle, a civilization can harness most of the light coming from a star by putting a structure around it. So we are using a small fraction of the light from the sun that is impinging on the surface of the Earth. And in fact, we are not taking advantage of all the sunlight. We're using just a small fraction of it. But if you cover the Earth with photovoltaic cells, you could in principle get all the energy falling off on the surface of the Earth. That's a small fraction, about 10 to the minus 8, 1 part in 100 million of all the light emitted by the sun. So if you imagine covering, making a sphere surrounding the star, and you could harness that energy. And Kardashev from Russia, he invented this scale that, there are different levels of civilizations. There is Kardashev number 1 and Kardashev type 2 and 3, depending on whether you harness just the energy falling on your planet or the entire energy of the star or the entire energy of a galaxy. And of course, the more energy is being used by a civilization, the easier it is to detect that activity. And so already there are limits in the literature on those Kardashev type 3 civilizations using energies from a whole galaxy, and also on Kardashev type 2 that use the energy of the star, because we can look for unusual properties of stars, and so far we don't have any good example for a Dyson sphere. There is nothing that was found, and frankly, it's a huge engineering enterprise if you think about it, because it's very difficult to support. I haven't been able to figure out an engineering approach to support a structure around the sun, that needs to hold itself somehow and against the force of gravity, against the very strong stress that is associated with the radiation falling on it, and the solar wind and all kinds of problems. So I'm not sure it's practical, actually. I mean, Freeman had good ideas, but some of them are out there,
What about an Alcubierre drive, though? Would we be able to see a different civilization using something like that?
In principle, yes. So astronomers, those that work on technological signatures, they write papers on limiting or limits on various types of technological civilization. But just to give you an example, the mainstream of the astronomy community is not really, there is a taboo. I didn't discuss it much, but there is a taboo on discussing technological signatures. I got a lot of pushback from astronomers to my suggestion that Oumuamua may be an artificial object. And I find that to be quite inappropriate, because I don't regard it as a speculation. I think it's quite likely that we are not alone and we just need to search. But a lot of my colleagues are not interested in having a discussion on this question. And that's unfortunate because there is no funding, not much funding for doing these searches. And also young people are discouraged because of the acidic atmosphere around this subject. And you may ask, why is the astronomy community so resistant to this idea, given that the public cares about it so much, and the public funds science, and the astronomers have the tools to search for technological signatures. And my guess is that it's because of the literature on science fiction literature on that does not follow the storyline, often does not follow the laws of physics, and because of the reports on unidentified flying objects. But my point is that if you go back to the Dark Ages, there were people claiming that the human body has magical powers, that it has a soul, and therefore it should not be operated. We shouldn't dissect the human body. And imagine scientists saying, we don't want to discuss the human body because there is all this nonsense being said about it. We would not have modern medicine if that happened to be the case. The whole benefit of science is that it can address questions that it has the tool to address using the scientific method. And therefore, the scientists have an obligation to address this question, given the importance of it for society. We need to find out in which neighborhood we live. And it's not just a neighborhood in terms of the stars and the dark matter, which have no relevance for our private lives. It's also a neighborhood in terms of other kids on the block. And we better find out using our scientific method. And I just find that the scientific community is exactly on the opposite side of where it should be on this subject. And part of my book is dedicated to this discussion. And I very much hope that it will change the culture. The book has been receiving a huge feedback from the public and the media. Within a week after appearance, it's everywhere. It's discussed everywhere. And to me, it illustrates the fact that the public cares deeply about this subject. And I very much hope that my colleagues will hear the message and will change their attitude, and that in the coming years, we will get more information, scientific information on this question.
So I have a really interesting follow-up question of a sort. Jared McQueen, PSW member, asks, how can we design special tools, space observation platforms that were more likely to detect anomalies like the ones that you discussed?
Yeah, that's an excellent question. So one way to do, really what we want is to get an image, a photograph of an interstellar object that looks weird, just like Oumuamua. And the one way to do that is to deploy spacecrafts that, they can be rather small and cheap, and to have a large enough number of them so that the next unusual object that passes by will get close enough to one of them. So if you have a large enough number of them hovering around, then one of them would be close to the path of an incoming interstellar object, and then you can take a photograph. That would be one way to do it. Another one would be to select all these interstellar objects on their way towards us and then intercept their orbit with a specialized mission that we send from Earth. But we should have a contingency plan and design such probes. The only way that this will not happen is if we listen to my colleagues that say it's never aliens, it's always rocks. And to me, they remind of a caveman that is used to playing with rocks all of his life, and then presented with a cell phone would say that object is a shiny rock. And it will be a missed opportunity if we don't examine all the objects that enter the solar system and look for the ones that look particularly unusual, because it saves us the trip. We don't have to go to interstellar space. They come to our backyard and we just need to examine them.
So I'd make a small comment here, which seems to me that the idea that we're unique is anathema really to the entire structure of science, because we assume the laws of physics are the same, the laws of chemistry are the same. We know the distribution of planets to some extent, and by golly, as you pointed out, there's an awful lot of them. They seem to have similar properties to the Earth. So it seems an impossible conclusion almost to assume that there isn't life elsewhere.
Exactly. No, that's exactly my point.
Outcome. And so, like looking for the Higgs boson, because it's a prediction of basic physical theory, we should really be looking for life elsewhere because it is a prediction of our basic understanding of the universe.
Yeah, that's exactly my point, that this is not a speculation. This is where the mainstream should be. And by the way, the public has its heart in the right place. So the public exercises exactly the common sense that you described, but the scientific community, the scientific culture, the academic culture is in the wrong place. And you ask yourself, why? And I have a simple answer to that. If you look at the theoretical physics, people are celebrating concepts like the multiverse, extra dimensions, string theory, supersymmetry. These are concepts that have no experimental evidence in their favor, but they are part of the mainstream. Why? Because in academia, right now, there is a culture that emphasizes a sandbox in which you can demonstrate how smart you are. So these concepts serve the purpose of measuring the intellectual abilities of different people, giving them positions or awards or honors based on how well they perform in this sandbox. The question of whether this sandbox matches reality is completely irrelevant. So there is this whole culture of physicists working on hypothetical concepts that have no relevance to reality necessarily, because we have no experiments that could test it. And it has the benefit that they don't put any skin in the game. They don't make predictions that can be falsified so that they will never be proven wrong. And that is a very comfortable position to be in. And so that obviously is a great place to be for keeping your image and not making mistakes. But if you go back in history, you find that Einstein, in his last decade of research, made 3 fundamental mistakes. He argued that there are no black holes, there are no gravitational waves, and quantum mechanics doesn't have spooky action at a distance. But he's still celebrated as one of the greatest scientists ever, because being at the frontier involves taking risks. You never know exactly where to go, and you make mistakes. That's part of the learning experience. But if you want to preserve your image, to show that you are smart, so that you can get into honor societies, get awards, if that is your motivation, you will try to avoid having some skin in the game, not to make mistakes, not to be tested. And being in this mathematical, fanciful world, is, to me, it's sort of like being high on drugs. That just you can imagine a virtual reality that exists out there without testing it. And unfortunately, that's a dominant part of the theoretical physics culture right now. And there are philosophers that justify. There are philosophers that we had at the Black Hole Initiative. We had the first annual conference in which a philosopher stood up and said, if physicists agree on something for a decade, then it must be right. And I said to him, how can you say something like that? The agreement of physicists has nothing to do with whether it's right or not. It's the test against evidence, the clues that we get from nature. It's a dialogue with nature. It's not a monologue. And you have philosophers justifying this activity. It all stems from the superconducting super collider cancellation. There used to be this project in the US that was canceled in the mid-1980s. And as a result, there were decades of stagnation in particle physics where no data came along. And then this culture developed. And so you see on the one hand, the mainstream endorsing these concepts that cannot be tested. And on the other hand, a concept of the existence of technological signatures is being bullied and ridiculed. And how can that happen? Something is unhealthy in academia right now. And I'm trying to change that. And obviously the public understands that. And if the public cares about the question, are we alone, more than it cares about extra dimensions or anti-de Sitter space, then that subject, anti-de Sitter space and extra dimensions, should be at the periphery of physics and the search for technological signatures should be center stage. That's
well,
my
we
point.
have a constructive question follow up to that. Do you have any propositions or proposals to reduce the societal derision towards the possibility of contacting extraterrestrial life? Which I would rephrase as, do you have any proposals as to how to, shall we say, reform the academic community so that they're no longer looking at this as some kind of an oddball and ridiculous endeavor?
Well, yes, I have a textbook that we wrote with my former postdoc Manasvi Lingam that will come out, will be published by Harvard University Press in half a year, the 25th of June, 2021, more than 1,000 pages long, that lays the foundation for the search for both biological signatures and technological signatures of life. And my hope is that research in this frontier will be based on what we describe in this book. And I think the main problem is in the way that the community responds to these challenges. And, you know, I very much hope that the culture will change, because I've been, you know, working on subjects that were not popular at the beginning, and then they became mainstream after a while. And, you know, I hope that by writing this popular level book and also the textbook that I just mentioned, the culture will change.
So we'll take two more questions, and then you're free to pursue your next interview or whatever this evening.
Thank you.
So, let me take the first one from the web. This is kind of a speculative question, and it's how might other civilizations be cloaking themselves? And do you think it's the JWST or LUVOIR will have a better chance of seeing them?
Yeah, so one thing, I mean, the astronomy community is coming up with those future observatories that will cost billions of dollars. And they are being motivated by the search, for example, for oxygen or methane in the atmospheres of planets around other stars as signatures of primitive life. My concern is that if we take the one example that we know of, the Earth, in the first 2 billion years, the atmosphere of the Earth didn't have much oxygen. It had microbial life, but it didn't have oxygen. So when you don't find oxygen, it doesn't tell you that there is no life. But if you find oxygen, it also doesn't tell you that you have life, because you can get oxygen from natural chemical processes. So you invest those billions of dollars, and at the end of the day, it will be debated forever about whether it's indicative of life or not. How can we be sure that there is life? If we find industrial pollution, if we find CFC molecules that are produced by refrigerating systems or industries that we have, those cannot be produced by natural processes. These molecules are too complex. So my point is, technological signatures could be much more conclusive. Why not put it on the table? Why not motivate these telescopes by the search also for technological signatures? Why is there a taboo on this subject? Makes no sense to me. Frankly, I'm speaking from my heart. You know, I speak straightforwardly, and I'm just using common sense, and apparently the public understands it. But I don't follow exactly why my colleagues are hostile to this discussion.
So I'll make two short comments, and then we'll take our last question from Tim Thomas, who's a member. And so the first comment is just to alert everybody that we're going to have a talk on the Giant Magellan Telescope in 4 weeks by the project manager for that observatory. And then subsequently in the coming months, we'll hopefully have talks on the 30-meter telescope and the European Very Large Telescope. And so we're now prepared to grill them on how they propose to use these telescopes to find, to look for signs of life elsewhere. And then I had a question for you, which is, are you familiar with this? I mean, NASA spent an awful lot of time and money looking into what biological signatures they could possibly detect. I mean, it's in that community, this is a very hot topic.
Yes, but primitive life.
Taking very seriously. And
yeah.
know that one aspect is recent discussion of a proposal by Lee Cronin along the lines you're suggesting, which is that he proposes a particular scale for determining the complexity of molecules, and says that above a certain threshold complexity, you can't find any naturally occurring substance. So if you can detect any substance with a complexity greater than the threshold, you have a bona fide sign of life. Yeah. So I wondered if you were familiar with that.
Yes, I'm familiar, and I know Lee Cronin quite well, and I heard him speak about it, and I agree. I mean, it's along the lines that I mentioned, except I was talking about going beyond the biology. He's mainly focused on life producing this complexity, but I'm focusing on artificial production that is industrial. Yeah, so my point is an extension of his, and it goes along the same lines. I agree.
So our last question is from Tim Thomas. Tim? Hopefully your mic is working.
Am I unmuted?
You are.
Yeah.
I'm wondering if Oumuamua was a technologically created thing, and we have to be prepared to look for the next one. How small a thing must we be prepared to look for? Seems unlikely that Oumuamua was the smallest object that would ever be sent.
No, that's an excellent point. So for example, the starshot probes that I described, they are much smaller. They are just a few meters in size. And my expectation is there will be a distribution of objects of different sizes and different speeds. And probably, you know, if there is a probe like starshot passing through our solar system, we would not know about it because it's too small, doesn't reflect enough sunlight for us to notice. Also, it's moving too fast for astronomers to call it an object of interest. You know, astronomers have something in mind. They have in mind near Earth rocks. So they're looking for things moving, you know, at tens of kilometers per second, roughly the size above that of Oumuamua, hundreds of feet. And that's what they're looking for. And they're not looking at things that pass close to the speed of light in front of their telescope. So I think, you know, if we are sufficiently imaginative, we would search for all scales and all speeds. And there would be many more small scale objects. And with respect to the speed, I have no idea. That depends on who produces them. So I completely agree with you that we should not necessarily focus just on the size scale of Oumuamua, because if you have more abundant population of smaller objects, they will come close to us. There would be many more of them, and therefore the nearest one would be even closer. And then even though intrinsically it's smaller in size, it might appear that it reflects more sunlight. So it all is, there is a competition here between the number of such objects as a function of their size. And, you know, and we don't know that distribution. So yes, we should search for objects of all sizes.
Thank you.
Thank you so much, Avi. Thank you for spending all this time with us. And thank you for stimulating us to really think about this. And we're going to write our senators and congressmen now to lobby for more funding for the search for.
Well, you know, I search for intelligence. I search for intelligence in the sky because I have a hard time finding it on Earth. But thank you very much for inviting me. It was a great pleasure, and thank you for your insights.
Hey, thank you. So thank you everyone for joining us tonight. And before you go, we have a few important notes. First, please join me in thanking our series sponsors, the Policy Studies Organization, in cooperation with the American Public University, and a donor who wishes to remain anonymous. The recording of tonight's lecture will be available to everyone on the PSW Science YouTube channel and in due course on the Vimeo PSW channel and via the PSW Science website. Please share the link with your friends and subscribe to the channel for notifications on new postings. And if you're interested in science and the society, please join. It's easy to apply for membership. Use the join button on the PSW Science website and follow the clear directions. We urge everybody to join, and we will welcome you to membership. The next lecture will be in 2 weeks on February 19th, 2021. The speaker will be Nicola Fox, Director of the Heliophysics Division at NASA. She will be speaking on the Parker Solar Probe and the closest encounter with the sun by any human-made object. On March 5th, Jim Fanson, Project Director for the Giant Magellan's Telescope, will be speaking on the GMT project and the GMT itself, which ultimately will have 10 times the resolving power of the Hubble Space Telescope and may well be as revolutionary in its observations. And on March 29th, Kate Kraft, planetary scientist at Johns Hopkins Applied Physics Lab, will be speaking to us about the Europa Clipper mission. This will be the second in an ongoing PSW series of lectures on missions to explore Europa and search for signs of life in its icy oceans. And also in May, and this date is tentative, May 7th, we will be having speakers on the Crossrail project, which is a project that constructed a new underground subway about 21 miles long, crossing underneath some of London's most built up areas, that was greatly facilitated by creating a virtual model of London and London Underground. All upcoming lectures will be posted in turn to the PSW website, www.pswscience.org. Check there often for updates. And last but not least, before you go, please join me in thanking tonight's crew, Anne and Robin, for producing this event. And I will now adjourn the 2,434th meeting of the Society. I wish everyone a good evening. The meeting is adjourned.